rising uniformly across the globe. We have to take factors into account such as currents or gravity. Satellites can also provide this information to give scientists more data that they can factor into their calculations. In some areas, the sea level is rising by more than 10 millimeters per year, while in others, it's going down more than 10 millimeters a year.
Sea level rise is a major indicator of climate change because it integrates a lot of parameters like, for instance, the melting of Greenland and Antarctica. We have an estimate of 3.1 millimeters per year over the last 25 years, but it's been accelerating in the last 5 years, near 5 millimeters per year. So it's a strong acceleration. By 2100, we could have a 2-meter rise of sea level.
Us humans try to mitigate the effects of sea level rise with infrastructure, like the dikes we see across the Netherlands. But the only real power we have against the rising seas is to examine the bigger picture of climate change and try to curb our emissions so that we can slow down this process of melting water, thermal expansion, and rising sea levels. If we don't make an effort to curb our emissions, it's not just going to affect our beach space, but impact the lives of hundreds of millions of people living in coastal areas who could lose their lands, their homes to the sea.
My name is Jérôme Benveniste. I studied math, physics, earth sciences in Paris, France, my home country. And I did a PhD specialized in oceanography from space in Toulouse. Most of the instruments we use in remote sensing are common to space exploration and Earth observation, and this is not surprising. What is remote sensing? It's just like, say, you want to know if the fire is hot. You don't need to touch it. You just put your hand in front and without touching the fire, you feel it's hot. That's remote sensing. If you shine light on an object, your eyes receive the reflection of the light and you see the shape and the color of the object. That's remote sensing. The sense of touch is much different. You need to touch to feel what you touch, so that's not remote sensing. Using the analogy of the ears and the eyes, we develop instruments that we use both for outer space and Earth remote sensing. And it's based on the electromagnetic radiation, either in the microwave band, like the cell phone frequencies or the microwave oven, or in the visible band, or infrared or ultraviolet. And this is why, if you learn everything about remote sensing, you can study the Earth, the solar system, the galaxies, the universe, and even beyond. Earth observation satellites go around the world in 1 hour and 20 minutes, so it's much faster than an oceanographic ship. It also repeats and repeats, and the observations are made for many years, typically 5 to 10 years. So you can imagine how fast we can acquire knowledge about the ocean, such as sea level, wind, waves, currents, temperature, salinity, thanks to gravity, and also the presence of algae and plankton. The ocean is vast and deep, and by snorkeling or scuba diving, you can take a look at the first 10 to 50 meters. But the ocean is 11,000 meters deep, so it's 1,000 times more. So making soundings from a ship is like launching a rope with a hook from a hot air balloon from above the clouds and probing to see what you can catch, like vegetation, a bicycle, an old tire, an umbrella, a cow, whatever. But from that, it's really hard to recompose what is exactly at the surface of the Earth. Well, it's the same for the ocean. And if you dive deep, like 500 meters, because of the pressure of the water column, you will need to decompress and on your way back. And that has to be done slowly, and it can take up to 3 weeks. So it takes 3 weeks to come back from 500 meters deep in the ocean, and only 3 days to come back from the moon, which is 800,000 times farther. And, it's 500 times the atmospheric pressure. Well, since the space era, we've been measuring sea level worldwide, globally, and before that, sea level was only measured by tide gauge in ports and just along the continental coast and in the open ocean at islands, but not everywhere in the world. With radar altimetry on satellites, we've been recording that sea level is rising. That's about 3.2 millimeters per year on average in the past 27 years. Well, thanks to the global picture that we can make with satellites, we can see that sea level is not rising everywhere. So this is a regional map of the mean sea level. So the resulting sea level rise on average is creating a much higher flood risk in case of storm surges and severely impacting the coastal and island communities through damage to coastal infrastructure, the agriculture, and even tourism and recreation activities. The World Ocean Day is taking place annually on 8th of June, and it fosters the public interest in management of the ocean, managing its resources, and keeping us on track with implementing the United Nations Sustainable Development Goals. And so keep an eye on the ocean at least once a year on 8th of June. And of course, every day, because, the ocean is supporting life on Earth. Once we have mastered the measurement of sea level in the open ocean with radar altimetry, we've put the limit to measure the sea level near the coast, which is more difficult, and in the estuaries, then in the deltas, and we went up in the rivers and lakes. So river discharge is really an important, what we call essential water cycle variable to understand the effects of global change. River discharge monitoring, day by day, is not only for climate, but it's also for predicting floods, which is the most destructive natural catastrophe. In the European Space Agency website at esa.int, you will find almost all the answers for which you have curiosity. And the ones that are not answered are the most fascinating ones, in fact, and we count on you to help answering them. And so have a nice time using space.
Hello, my name is Kate Underhill and I'm a rocket scientist with the European Space Agency. I studied physics and space engineering back home in the UK, and now I'm based in Paris at ESA's Space Transportation Directorate. And today I'm going to be answering questions from all over Europe about rockets. So let's see what our first question is. Could you describe a rocket launch step by step? To start at the beginning, at least for ESA's rockets Ariane and Vega, many parts of the rocket are built in Europe, from all over Europe, and then shipped across the Atlantic Ocean to Europe's spaceport in French Guiana. French Guiana is a really good place for a launch base because we've got lots of room to do our activities, because it's on the coast of South America, so we can launch over the ocean and not over people's heads, because there is not many earthquakes down there, so we don't have to worry about them shaking up our rockets, and because it's near the equator. And with the Earth's rotation every day, that means that our rockets are already going at 1,500 kilometers an hour before they even take off. So all the parts of the rocket are shipped down to French Guiana from Europe. Some parts are built there, are made there, like the solid boosters of Ariane 5 or the first stage of Vega. Then the satellites we're taking into space are built all over the world and flown into French Guiana, and we assemble all these elements together. Put the rocket bits together, put the satellite on the rocket, and then we put a protective cover on the satellite called a fairing. Now there are so many bits of a rocket because a rocket is made in stages, and why we have stages is because to get into space a rocket needs to be going really fast. It needs to be going at nearly and over 8 kilometers a second. In order to do this we have to burn a lot of fuel, but the more fuel we burn the heavier the rocket is, and the harder it is for the rocket to get off the ground in the first place. So we do it in stages. A stage is ignited, it burns up all its fuel, and then as soon as the stage is empty, it drops back down to the ground, and the rest of the rocket, the other stages, keeps going up into space. And we do this in as many stages as we need until we get up to the final speed we want. Now this staging principle is shown by this anemotastic graphic of a Vega rocket. A Vega can take the equivalent of a Hippo into space, a satellite of up to 1.5 tons. Now, once we're in space, and to get the Hippo, our satellite, to exactly the right position, we need 0.5 tons, or a polar bear's worth of fuel in the last stage. Now, to get that polar bear and that Hippo up through the top part of the atmosphere and into space, we need 2 elephants worth of fuel, 11 tons of fuel. To get 2 elephants, a polar bear and a Hippo up through most of the atmosphere, we need a Camarasaurus worth of fuel, 24 tons. And to get a Camarasaurus, 2 elephants, a polar bear and a Hippo off the ground in the first place, we need a huge amount of fuel and a huge amount of power. We need 88 tons of blue whales worth of fuel. That's nearly 300 times more fuel in the big first stage that takes us off the ground than the light top stage that maneuvers us in space. We have built the rocket together, we've assembled the stages, we've checked everything is right, we're happy with the rocket, we take it out to launch pad, then we get the green for the final countdown. 3, 2, 1, lift off. The first stage engines ignites and the rocket takes off in a boom of noise and light. So the rocket flies up on a trajectory or a path to space that we've predefined for it. It goes vertical at the beginning and then lifts over horizontal in a maneuver we call a gravity turn. It rushes through the atmosphere, and then as soon as out of the atmosphere, we can drop the protective fairing around the satellites because there's no more air drag on them. Then it keeps flying upwards, dropping stages, each time one of them is empty of fuel, and then eventually getting to space and getting to position where it releases the satellites into the places they need to be, and then the final stage of the rocket will maneuver itself into a safe orbit to avoid any kind of collisions with any other spacecraft. So let's see what our second question is. How fast can a rocket go? Now this is a really great question because how fast a rocket goes is linked to what the satellite is going to do that it's taking into space. So for example, Europe's Ariane 5 took the Automated Transfer Vehicle, the ATV, to space so it could deliver supplies to the International Space Station. In order to get to the space station, Ariane 5 gave the ATV a speed of 7 kilometers a second. The ATV was 20 tons at liftoff. If we want to go a bit further up, so for example, geostationary orbit where all the telecommunication satellites are, 36,000 kilometers up, then the rocket needs to give that satellite 9 kilometers a second to what we call a geostationary transfer orbit that will set it on the path to its final destination. Ariane 5 can take 12 tons up to 9 kilometers a second. If you want to go even further, so to the moon for example, then we want to go on what we call a lunar transfer orbit, again on the path towards the moon. And to put a satellite on a lunar transfer orbit, then the rocket needs to be going at over 10.5 kilometers a second. And this is what Europe's new rocket, Ariane 6, will be doing when it delivers a lunar lander around the moon. Now, if we want to go even further, we have escape orbit. This means leaving the gravitational attraction of the Earth and going out into the solar system. In order to reach an escape orbit, the rocket needs to be going at 11 kilometers a second. This is exactly the speed that Europe's Ariane 5 gave the Rosetta Comet Chaser mission back when it launched it in 2004. Our Rosetta was only 3 tons at launch. And so for our last question, I'm being helped by Tom here. Tom, what's the last question? Can a rocket lift off from another planet? This is another great question. And the answer is yes, of course it can. And in fact, we've already done it. When the United States landed on the moon over 50 years ago, the craft they landed on was in 2 parts. One part that stayed on the moon, the second part lifted them off the moon and into orbit and back home to Earth. This is what I love about rocket science and about science in general, is the same rules apply everywhere. The rules we have today for designing and building rockets apply wherever you want to launch from. All you need to know is that the heavier the planet you're on is, the harder it is to get into space. But To make all these ideas a reality, to launch from Mars, to make our own propellants, we need new rocket scientists like Tom here and like you to make these ideas a reality.
Though it's been 50 years since humans first stepped on the moon, we haven't forgotten about Earth's natural satellite. Several missions since Apollo have taught us so much about the moon and have paved the way for humankind's return. I'm Alana Bartolini from ESA Education, and here with me today to tell us a little bit more about these missions and future exploration of the moon is Dr. James Carpenter. James, thanks for joining me.
Hi.
So to start off, can you tell us a bit of a summary about moon exploration so far?
The moon, of course, is our closest celestial neighbour. It's something that humans have looked at and tried to understand forever, right? But then lunar exploration really began in the 1960s and 70s, where we had robotic and human missions going to the moon. From the lunar missions from the Soviet Union, which roved around on the surface and returned samples. But then really the pinnacle of this was Apollo, and the first and only time in history that humans have set foot on another celestial body. Now, that was not a scientific program. It wasn't done to create new scientific data. It was done for a whole set of other reasons. But at the same time, it was really transformative for science. So what we learned from the samples that came back from the moon was the origin of the Earth and the moon as a system that has a common origin. We learned that the moon has been an archive of solar system history, that the moon is the only place where we can go to learn about the history of our own planet, especially in the early periods that have been lost from our own terrestrial geology. So this was really transformative for our understanding of how planets form and evolve, and become the basis for planetary science and much of what we know about our own planet too. So that's something which started in Apollo and has gone on since then. So people are still using the samples that came back from Apollo 50 years ago to do new science, and that's something that's really taking off again in the present time in recent years. At the same time, after Apollo, we had this period where not a lot happened on the moon. It was very quiet. There weren't any missions there. The moon was quiet once again. And then the last few years, we've had this renaissance of lunar exploration. We've had new missions from the United States and from Europe with Smart 1, and then more recently from China and from India and Japan. And so these new missions have created a wealth of new data, which have really given us a global context for what came before. So we're now starting to understand everything that we've done before with these samples and these early missions to the surface, but really in a global way, finding out what this means in a broader sense, and how we can interpret that better. It's also taught us that even though all these samples, all this science that was done in the past is the basis of so much of what we understand about the history of the early Earth and the planetary formation in general in the solar system, it's very incomplete. That the moon is a large place, has tremendous diversity. We've really only scratched the surface.
So taking all of that into account, what are the next steps? What's in store for the future of moon exploration?
So I think what is coming is very exciting. We have multiple countries, multiple agencies, and people outside of agencies in the private sector, people who are not from space agencies, but really have their own either businesses or their own fortunes, people who are very, very wealthy, who are trying to explore the moon now. India tried to land this year. They didn't succeed, but they have an orbiter now going around the moon, and they plan future missions. A private sector mission from Israel tried to land on the moon earlier this year, was not successful, but that also was the first time a private sector company had tried to get to the moon. We have missions from China, so China landed on the moon this year, the first ever Farside mission, and they have big plans for the future, involving the establishment of a lunar research station, robotically initially, and then moving to humans over the next decade or two. And then in NASA now, in the US, we have the Artemis program, which is intended to bring humans to the lunar surface again for the first time since the Apollo era, and this time in a different way. So we'll be looking at doing science, exploring places that have never been explored before, but also exploring things like how we can use the local resources that we find on the moon to enable permanent, sustained and sustainable exploration, to learn how we as a species can live and work away from our own planet. And we in Europe have a vision for exploring the moon, which is one about partnership and cooperation. So we want to deliver science, we want to prepare the future, we want to create the technologies and capabilities by integrating science and technology together that prepare us for exploring the solar system beyond the moon, but also establishing sustainable exploration of the moon for the benefit of humanity. And so we are working in particularly with the United States, with NASA on the Artemis program, and we're very excited about the contributions that we're making to that and the developments that we're making in the coming years.
So one of the questions or things that we sometimes hear is, why are we going back to the moon? What are some of the reasons that we should continue exploring the moon?
Okay. So the moon is an archive of solar system history. On Earth, we have plate tectonics, we have water erosion and wind erosion, and this has removed the earliest periods of geological history of our planet from our own planet. Now the moon has remained geologically very stable for a very, very long time. And so as the sun has changed over time, as comets and asteroids have bombarded the inner solar system, as our solar system has moved through the galaxy, going through the spiral arms, through dust clouds, near supernovae, all of these events have had an impact on the inner solar system, and all of these events are recorded somehow in the surface of the moon or in the moon somewhere. And so by accessing the moon, we can find out about the history of our solar system, of our own planet, and about all of the things that have happened there over eons of time that have been lost from our own geological record. At the same time, the moon is a place where we can learn what it means to live and work off-world. So there are resources on the moon that we could conceivably use. So we now know that at the poles of the moon we have very, very cold places that never ever see the sun. And these are some of the coldest places in the solar system, and we know that in these places now we have water, ice, and other we call volatile chemistry. This is the chemistry that creates the building blocks of life, but it also can be useful. So water is oxygen and hydrogen. Oxygen is useful for humans, and oxygen and hydrogen together are rocket fuel. So we could conceivably have a store of fuel at the surface of the moon that we could use to explore beyond. At the same time, the minerals around the moon are made of oxygen, metals, and silicon. And if we could find a way of separating those things, then we have oxygen, which again is useful for life support, but also for propellant, for fuel. And we have metals and things you might be able to use for manufacturing on the surface of the moon. We go to the moon to understand the moon and what it can teach us about planets. We go to the moon to understand what it can tell us about the history of our solar system and our galaxy and our star and the planets in the solar system. We go to the moon to understand the origins that we share between the Earth and the moon. And we go to the moon to use that as a platform to look outwards beyond. And we go to the moon to understand how we as a species can live and work off Earth in a sustainable way to prepare future exploration, but also to understand better how we can live and work sustainably here on Earth.
And so, James, you're a moon scientist. How did you get started in lunar research? Did you think that you would be working to get humans to go back to the moon?
So if I told my 9-year-old self what I was doing now, my 9-year-old self would be very excited about it. I think that when I was a child, I was really excited about space and exploration. And then I reached my teenage years and it stopped being something that had any meaning because I didn't see this as something that was realistic. It was a childhood fantasy, if you like. And then it wasn't really until I was about 16 when I suddenly realized that this was a real thing. That even here in Europe, there were people that did this for a career. There were things that were happening here. And when I learned that, I had to do it. So I studied mathematics, physics, and chemistry at A-level, which were the qualifications we had in the UK at that time. And then I went on to study physics with space science and technology for a degree. I did my PhD, and then after some years working on space projects in the UK, I came to the European Space Agency to support future exploration missions. And I think now is a really exciting time to be here and working on this because I think we are at the beginning of something that is going to be very exciting, very future looking, which is really going to be international and where Europe and we in the European Space Agency and where the people of Europe can be very, very involved. And I think if you are a student or a child today who is interested in space, there has never been a better time because when you are leaving school and when you are going into the workforce, these are the things that are going to be happening. We are going to be going to explore the solar system. We'll be doing that as a species in cooperation, and there are extraordinary opportunities waiting for you.
And with that wonderful sentiment, I want to thank you for being with us here today.
Thank you.
To all of you watching, thank you very much for watching this series. I hope that you have enjoyed learning about the moon with our ESA experts.
Hello world, my name is Stijn Tole and I'm ESA's research doctor here at Concordia Station in Antarctica, and I'll talk with you a bit more about how it is to live in isolation here. So Concordia Station is one of the 3 stations in the middle of the Antarctic ice sheet operating year-round for science. For a 9-month period within this year, it's not possible for any transport to get in or go out of the station because of the extreme conditions outside. So I arrived here 5 months ago as part of a 12-member crew to stay for this winter period to maintain the station and continue with science. The main goal of my mission is to implement biomedical research experiments on myself and on the crew. And these experiments have been selected by ESA to learn more about how this environment can be a risk to our body and our mind. You can imagine if we want to plan for future manned missions to the moon or to Mars, it's important that we understand these risks better. Because if we go to space, we have to deal with all kinds of stressors. Deviations from the normal situations, you could say, that ask our body and mind to adapt. And this can have quite some consequences for our health and also for our performance. Think for example about bone and muscle loss, if there's a lack of gravity, or space radiation if we go further into space. It can have serious long-term consequences as well. But also not being able to just go back home if you want to. Being isolated and confined in a small crew and not being able to go outside because the conditions outside are too hostile. This is where Concordia is interesting. So Concordia is quite such an environment. Here we live with 12 people for 9 months without any possibility of rescue. And we are at altitude, so there's less oxygen to breathe in the air. And outside temperatures can go as low as minus 80 degrees at one point, and there will be a time period of 3 months without any sunlight. So in that sense, Concordia classifies as we call it, isolated, confined and extreme environment, which has many similarities with space. It looks a little bit like living in a future space habitat. So the experiments that we're going to perform this year here look into changes in blood volume, changes in our immune system and in our gut bacteria, and how they can impact our health. But also we look at eating behavior, sexual feelings and well-being, and mindfulness, which can maybe be helpful to help us adjust to a strange environment like this. So prolonged isolation can have a psychological effect on us if we fail to fully adjust to this new environment. And you can imagine that's not so easy. It has been described in people that overwinter in Antarctica that they can develop symptoms of tiredness or headaches or sleep problems or problems with attention and memory. But also you may start to feel depressed or more anxious or angry, and there may be conflict between people in the base or even with people back at home. Usually you see that these kind of symptoms are more present during the harsher middle of the winter when the stressors are higher. But if we then talk about long-term effects, you also see when the stresses get lower and when, for example, the sun comes back, the symptoms get less as well. So we call it therefore the winter over syndrome. But most important, I think, is that overcoming and sharing these challenges together, of overwintering in Antarctica, can also come with a sense of accomplishment. And you see that people going to Antarctica often see this experience as a very important one in their life. It can come with more self-esteem, we may become better in solving problems and even feel closer together and get a better understanding of each other. And to me, this is the reason that I came here, because I think this is a very valuable experience. Living in isolation, personally, I think it can be helpful to try to create an environment that is a little bit more like at home. So for example, here I try to maintain a daily rhythm that mimics the day and night, even if there's no sun outside. And I try to stimulate my body with exercise, even if it's not possible to go outside and do my favorite sports. I also try to keep eating healthy with the idea that all these stressors is something our body needs to deal with and it could use some good food. Staying in touch with the people at home, with my family and friends, for me it helps a lot. And sometimes I actually do go outside, for example when I've collected samples, such as stool samples, saliva samples, blood samples, and these samples need to be stored cold, so lucky for me that I've got a big freezer outside. But more important maybe is also to understand that even though this is a new environment, it doesn't necessarily need to be an unpleasant one. I try to focus on things that I can enjoy myself with during my time here, such as new hobbies, and I might set new goals. And then if we are living with other people, especially if those people are not the ones you choose to live with, like here, I think it's important to be very tolerant as much as you can. And it's not always easy, especially when the stresses are high. We tend to think first about ourselves. But to look into the perspective of the other person, I think here is very important.
Hi, my name's Kate Isaac. I'm a physicist and I work at ESTEC, which is in the Netherlands, and it's the technical centre of the European Space Agency. I work on a science mission called CHAOPS. CHAOPS stands for Characterising Exoplanet Satellite, and what we're going to do is to measure very precisely the sizes of exoplanets that have been found by other people. The Earth, Mars, Jupiter and Mercury are all planets that go around or orbit the Sun, which is our star. These are 4 of the 8 planets in our solar system. An exoplanet is a planet that is outside our solar system. It is typically orbiting a star, although it doesn't have to be. As of July 2020, we know of more than 4,000 exoplanets that have been discovered in searches that have taken place both from the ground and from space, using space missions that are operating above the Earth. These searches have found many unexpected types of exoplanets and have produced many surprises. Many planets that are very different from those that we are familiar with, planets much smaller than the Earth, larger than Jupiter, the most massive planet in our solar system, also the largest, as well as planets that are much hotter and much colder than anything we have in our solar system. Planets with temperatures higher than molten lava inside a volcano and higher than the melting point of iron. The first exoplanet discovered orbiting a star similar to our own Sun was discovered in 1995 from the ground. 51 Peg b has a mass of about half that of Jupiter, but that's where the similarity stops. It's orbiting a star called 51 Pegasi, which is reasonably bright as stars go, but still not quite bright enough to be seen by our own eyes when we look up at the sky. The planet has an orbital period of just over 4 days. This compares with an orbital period of the Earth, which is 365 days or 1 Earth year. So 1 year on 51 Peg b is much shorter than that on the Earth. The planet is much closer to the star, which means that the planet is very hot. It is in fact more than 4 times hotter than the Earth is. Although to date we have found more than 4,000 exoplanets, we still haven't found one that is exactly like our own Earth. We are continuing to look, of course, but in the meantime we're trying hard to understand more about what we've already found, about the exoplanets that we've discovered to date. We ask ourselves, what are they made of? Are they rocky? Are they icy? Are they big balls of gas? Also, what we would like to know, and what we're interested in finding out, is how they were born and how they age, as well as whether they have atmospheres like our own or Earth. All the time we're thinking in the back of our minds whether there is an exoplanet out there where in the future we could possibly look for and find signs of life. Travelling to an exoplanet is not possible today, as even the nearest ones are much too far away. It would take light more than 4 years to travel from the Earth to the nearest exoplanet we know of, which is in the Proxima Centauri star system. As of today, we can only travel at a very small fraction of the speed of light, and it would take us tens of thousands of years to reach the exoplanet. This is much longer than a human lifetime, much longer than the lifetimes of many human generations, in fact.